Welcome to this explainer. Today, we're going to look at our skylines just a little bit differently. We're actually going to treat the skyscraper like a living organism. Why? Well, to understand exactly how we can solve the massive energy crisis that's currently looming over our cities. It's a truly fascinating shift in how we think about architecture, engineering, and sustainable urban design.
To really wrap our heads around the scale of the problem we're trying to solve here, take a look at this staggering number: 40%. The buildings around us right now consume up to 40% of all global energy. Plus, they're responsible for roughly 33% of the world's greenhouse gas emissions. They are incredibly hungry for power, and frankly, their environmental footprint is massive.
And guys, we are very much on the clock. The United Nations Environment Program has made it crystal clear. We absolutely must drop energy intensity in the building sector by 37% by the year 2030 compared to 2015 levels. What that boils down to is that business as usual is simply no longer an option if we want to hit our global net zero targets. We need a fundamental rethink of how we build.
Which brings us to Section 1, Beyond the Rooftop and the Skyscraper Dilemma.
Right off the bat, there's a pretty stark contrast between a standard low-rise house and a towering skyscraper. This is where the traditional solar math completely breaks down. You see, low-rise buildings have abundant roof space relative to their overall volume, along with a pretty low energy demand, making standard rooftop solar highly effective. But high-rises? They have this tiny roof footprint compared to a massive vertical volume and an immense energy appetite. Honestly, even if you covered every single square inch of a skyscraper's roof in the most efficient solar panels on Earth, it would barely make a dent in its daily needs. That means we have to look beyond the rooftop.
Let's dive into Section 2, the heat harvesting secret.
It really all starts with this one fundamental question. What actually happens when solar panels get too hot? When standard photovoltaic cells absorb sunlight, they don't just create electricity. That surplus energy heats up the panel surfaces. And this is a critical problem, because as they heat up, their electrical efficiency actually drops, and the intense thermal stress significantly reduces their operational lifespan.
So how do we solve this overheating issue? Well, the answer is BIPV/T, or Building Integrated Photovoltaic-Thermal systems. You can think of this as the ultimate two-for-one solution. The technology is integrated directly into the building's exterior. It actively pulls that excess heat right away from the solar panel, which instantly makes the electricity generation more efficient. But here's the best part. It doesn't waste that heat. It actually captures it, banking that thermal energy to provide the building with free hot water and winter space heating.
Now, check out the anatomy of a modern heat pipe system here, capturing that excess thermal energy. Early water-based systems required this messy, complicated plumbing right behind the panels that was super prone to freezing or leaking. But this newer heat pipe design transfers the thermal energy directly to a condenser for collection up at the top without needing a continuous flow of water across the entire back of the panel. It's just an incredibly elegant, robust way to harvest that surplus heat.
All right, moving into Section 3, Building a Smart Skin.
Just look at these advanced architectural blueprints. We're literally transforming static, dead walls into a living, smart skin. Engineers are now utilizing curved water-based panels for roofs and balconies, integrated refrigerant channels, and double-skin facades with ventilated windows. The building envelope essentially becomes a breathable, energy-harvesting membrane. It isn't just a wall anymore. It's an active, working part of the building's energy ecosystem, capable of adjusting to the sun and capturing energy from every single angle.
But the benefits extend way beyond the walls of the building itself. Not only do these smart skins power the building inside, but they also act as an environmental shield. By actively absorbing that intense solar radiation and converting it into electricity and usable heat, rather than just reflecting it back into the atmosphere, they actually help lower the building's exterior surface temperature, and this, in turn, helps cool down the sweltering streets of our dense urban environments, actively combating the urban heat island effect.
Now for Section 4, Storing the Sun's Energy. To actually build a complete storage ecosystem, we've got to map out both the thermal and electrical solutions. Doing this allows us to bridge the gap between peak generation and peak demand, tracking everything from standard batteries for electrical storage all the way down to highly advanced ground thermal energy solutions.
breaking down the thermal side of that ecosystem, we have a handful of really powerful mechanisms at our disposal. We can bank this heat using highly insulated water storage tanks for direct domestic use, or we can use sensible heat storage, like trombe walls, which are these massive structures that passively absorb heat and then slowly release it into living spaces. There's also ground thermal energy storage, which uses heat pumps to balance soil temperatures across the seasons, and perhaps the most advanced are phase change materials, or PCMs. You can kind of think of these like smart ice cubes that physically melt to absorb heat and freeze to release it, keeping temperatures perfectly stable.
Finally, let's zoom out for Section 5, the net zero skyline.
There are 3 foundational steps to achieving a true net zero energy building. This really acts as the master blueprint for tomorrow's architecture, showing exactly where these BIPV/T smart skins fit into the ultimate goal of decarbonizing our world.
The reality is, you simply can't achieve net zero unless all 3 of these steps are working in total harmony. Step 1 is optimizing the building's geometry and orientation so it naturally heats and cools itself as much as physically possible. Step 2 requires using hyper-efficient appliances, HVAC systems, and lighting to drive overall energy demand down. And finally, Step 3 is wrapping that highly optimized structure in a BIPV/T smart skin with robust thermal storage, allowing the building to generate all of its remaining required power and heat entirely on its own.
Which leaves us with this final, honestly pretty remarkable question to ponder. If every skyscraper became its own power plant, what would our cities look like tomorrow? Imagine walking through a metropolis where the massive glass and steel towers aren't just aggressively consuming the grid's energy. Instead, they're silently acting as a vast, interconnected solar engine, powering the world around you while keeping the streets cool and the air clean. That is the incredible promise of the net zero skyline. Thank you so much for joining me on this explainer. I really hope it sparked your curiosity and changed how you look at the buildings all around us.